Okay guys, so let's get started with the same thing we left off previously, influence lines diagrams. We were doing influence line diagrams for reactions last time. You're going to submit your assignment Monday, yeah?
Yes, sir.
Okay, Monday. Yes, so yesterday we did influence line diagrams for reactions. Today we are going to focus on shear force and bending moment diagrams. Okay? So again, the important thing to appreciate is that influence line diagrams for all these variables of interest, like for example your bending moment, shear force or reactions, they are all linear. Okay? So if you want to draw the influence line diagram for shear force and bending moment, please make sure that for determinate structures they are always linear. And in your case, in your course, I mean, it will always be linear. Okay? So the influence line diagrams for let us start with a simple problem and discuss the influence lines accordingly. Okay, so the simplest problem we can have is of a simply supported beam where we have got a say section 1-1. So, in case of a simply supported beam, we have got a simply supported beam case where, and imagine we are interested in finding out shear force and bending moment at point C. Okay, so how are we going to determine it? Yes, so sir, excuse me, so what are we after? No, what in this case, what are we doing?
We are going to draw this time.
Yeah, for what? Influence line diagram for which section? No, I'm asking him. Okay. For which section? We are trying to develop influence line diagrams for section CC. Okay, and the influence line diagram for determinate structure are going to be? Sir, I'm not asking you, I'm telling you. I'm asking him. Okay, so please, yes, influence line diagram for determinate structure is?
Always be linear.
Always be linear, yes. And in the case of reactions, for example, if we are trying to find out reactions for a particular beam like this one, okay, so where do you assume the maximum reaction is going to be? For example, yes, in the previous class we did that. Where do you think the maximum reaction is going to be? Did you come yesterday? Yeah? So you were again scrolling? Yeah? Moving up and down, scrolling? We are trying to find out the influence line diagrams for section C. Okay, the influence line, the bending moment and shear force influence line diagram for section C. Now, what's the first step we do? What the first step we did previously in the case of reactions? We remove the ability to resist that particular variable. Okay, that particular quantity, the ability to resist that, we remove that. So in the case of reaction, what happened? We had a support, and support will normally resist the reaction. Okay, so we remove the support. Now similarly, we in the case of shear force, we have to remove the ability of this section to resist shear. And what do you reckon? How can we do that?
Sir, by applying shear force,
Hinge?
internal hinge
Internal hinge
will not support the shear force.
No, internal hinge will always support the shear force. Internal hinge releases moment. Yes, in the case of moments, yes, the internal hinge will. The internal hinge doesn't take any moment, isn't it? So it will. So in the case of moment, yes, we have to place an internal hinge. But what do you think in the case of shear? No, reaction is different. Reaction is taking care of your. You mean remove the reaction? You mean remove the support?
Yes, exactly.
So if you remove the support, then you are removing. That's actually for reactions. That's not for shear force. Removing support is not going to make any shear force over here zero. So what should you do? Well, how does the shear force act normally? We have got shear force. Look, let's imagine how does the shear force act. Sir, how does the shear force act, sir? What is normally the sign convention of shear force? Positive. Sir, I've taken the attendance, okay? I've taken the attendance. So, because like my eyes will again keep on falling on you and you will keep on scrolling and scrolling and scrolling. Look, you're wasting our time. That's my weakness. I'm sorry, I apologize for that. But the thing is, I want full concentration. And you will be distracting me. So if you are not interested in the lecture, I've taken the attendance, your name is there, you can leave the class. Because then that will cause distraction. Look, this is the second time I'm spending and you are still looking into your mobile. Yes? So that's a distraction for you, okay? So if you are not interested in the lecture, no offense, okay? No offense. You can please leave. Now we have your attendance marked, okay? So if this is, obviously it is for attendance, isn't it? Yeah, or you're just enjoying the room. So the thing is that you have shear force. If you cut any place, what happens is that your shear force will be something like this. Yes? And similarly, if we have moment at this particular section, so that will be something like this, isn't it? That's what our assumption is. Normally the moment is in this direction and the shear is in this direction. Okay? Do you agree, sir, with me? Do you agree with me that normally when we draw shear force or bending moment diagrams, this is our normal assumption, isn't it? If we cut it over here, we will have shear force in this direction and we will have moment in this direction. Now, in your opinion, what should we do to release this sort of thing? I will just use your common sense, okay? What should we do to release this sort of thing? I mean, in the case of moment, as we discussed, not to have these two moments appearing, you provide a hinge. So what should you do to release something like this? How? Don't you think that if we provide something like, look, okay, if we provide something like this, would this shear be released? No. I mean, like, okay, remove this thing. Okay? Remove this. Now, if I provide something, a release like this, and so what do you think? Can this instrument take any shear?
No.
It can't take any shear, can it? So that means that if we provide something like this, that will actually release our shear, isn't it?
Yes.
Now this thing can take moment. If I can apply moments, isn't it? I can apply moment, can't I? But I can't apply any shear. Do you understand my point, sir?
Yes.
Yeah? I'm not picking on you really, but I want to develop your interest, that's it. Okay, so if we have something like this and we apply shear force, it's not going to take any shear force. Yes. It will take moment. Why? Because what is moment? Yeah, I'm trying to apply tension at the top, my index, and compression at the bottom. Yes. So it will take moment, but it's not going to take any shear. Yeah. So in the case of shear, we should have this sort of gadget. Do you understand my point?
Yes, sir.
Yes. Yes. Yes.
Can we develop this type of gadget by applying two hinges?
No, not two hinge. If you provide two hinges, that will make your moment zero.
Yes.
So if you have two hinges like this gadget is actually it looks something like this. It has got rollers in the middle, and we can have shear in this direction, but it takes moment. Yeah, and in this case, we provide an internal hinge like this one. Agreed? Yes? Any question? Okay, so now this thing we will apply. So imagine we apply it over here. What will happen is, if you put it over here, what will happen? Now you have got this thing, okay? What does the Muller and Bruns law principle say? That you take that gadget, you release that particular action, so which is in our case shear, okay? That internal force we release, the ability to resist that force we release, and we put it in that particular location, okay, that gadget, and then we allow displacement at that location, and the actual deformed shape is the influence line diagram, isn't it? Yes. So what will happen if I put this thing, the same instrument over here? What will happen if I put it over there? So I put okay, so if I put it over here, what will happen? This portion will move down, the other portion will move up, and I will have something like this. Would I have something like this? Do you agree?
Yes.
Yes.
How that side portion will go up?
Because you have got another shear in this direction. That is the definition of shear, isn't it?
So
shear is, look, your shear, this is moving, let me move. Okay, so shear always comes in parallel, isn't it? Yeah, one side is moving up, another one is moving down, isn't it? So if I put it over there, this is moving down and this one is up. So this will push this thing up and this one will push this thing down, isn't it? Or no? Question. Shear always come in pair.
sir, it may be exactly opposite, like that side goes up and this side goes down.
But this is our sign convention. Based on, if you want to adopt a particular sign convention, then you stick to that. So this will always move in the direction of your assumed sign convention. If you have assumed the opposite sign convention, then it will go opposite.
Sir, but I was assuming that there may be some longer side or some that thing.
What do you mean? The longer side doesn't have any influence on the shear.
Okay, sir.
The side length doesn't have any influence on the shear. Shear is always summation of all the forces in y direction towards normally the left we take. Okay, so all the forces which are in y direction towards the left of a section, and all the forces which are towards the summation of all the forces which are towards the right of the section. Yes. So yes.
Information ही है इसमें बहुत ही
You haven't got that? देखिए, first thing is what happens when we have a shear at a particular section. So we have P applied on this section, agree? So what happens is, what is the shear force diagram? The shear force diagram, that is the static case. We are talking about the shear force diagram, okay? That goes like this. Over here we have one shear and then we have another shear. Isn't it?
yes
There are two shears at this point and then it goes and comes down. That's why we have this jump. Because of the two shears. You have got one this shear and one that shear. So obviously the shear values are going to be twice, okay? And they are going to be equal and opposite. Yes, we have two shears. So what I am saying is that in order to release this thing, in order to release the shear at a particular point, you place this gadget at that location. Now, according to our sign convention, everywhere, if I cut this, everywhere I will have shear like this and moment like this. Shear like this and moment like this. That's what we have done previously, isn't it?
yes
We have so you have got one shear in this direction and one shear in that direction. So when you place this gadget at this location, this shear will try to move it down and that shear will try to move it up. So that's what has happened. I've placed it over here. This portion has moved down, that portion has moved up.
so what do we call this gadget? What's the name of this gadget?
Well, this is called a guided support. Normally, these are normally, but this is, look, Muller and Brusler principle, that is just for drawing influence lines. This is not actually a real support which you are placing over here. You are drawing your influence line diagram, okay? You can also do something like, you know, if you want to derive your or draw your influence line diagram from the first principle, what did I tell you? You can have a load moving and you keep on finding your shear at different location and then keep on populating and all these magnitudes and you will get an influence line for shear force diagram. Do you understand my point? So I can have a unit load being moved along the span and I keep on finding the shear, okay, and the moment it crosses over here, there is a jump in shear, isn't it? Yeah, the moment it crosses C, there is a jump in shear. So that's why I got this jump over here.
Sir, we have applied unit load at the point C.
No, this is influence line diagram. We are running the unit load all along the beam. This is not the shear force diagram. In shear force, the location of the load is constant. But in this case, the location of the load is changing. Okay, so this is all this influence line, what you get, that is telling you what will be the shear at point C when you make the load run along the whole beam. Do you understand my point?
Yes.
So what you have is that we place this thing doesn't take any shear, so one portion of it will move down, another portion will move up. Okay, so that is our shear. So beside this, we assume that if in the case of shear, we say that if it is below, we say that if it is above the axis, this is positive. If it is below the axis, it is negative. Okay, so that means that this is a positive shear, this is negative shear. Okay,
Yes, sir.
and however, in the case of moment, what do we do? In the case of moment, we say
Clockwise positive.
No. We are saying that if it is in this direction, it is positive. If it is in this direction, it is negative.
It didn't make sense.
We are not, sorry, I'm just saying that in the case of moment, we can assume that if your moment is over here, then you take positive. So what this assumption is going to do is you will always draw your moment on the tension side. Okay, what you have done is previously you give your moment diagram, your positive was in this direction, isn't it? So when you had a moment which caused sagging, you considered that as positive. So that positive, you assume that it is like this. But I can assume that my positive is not this one, is this one. So I just draw it like this. But what will happen is that its deformed shape and the moments, they will be in the same direction. Okay? So does it make sense?
Sir, there is a question.
Yes.
सर जो लोड हमारे पास मूव कर रहा है उसकी पोजीशन हमारे पास जो हमने सेक्शन काट दिया है उसकी पोजीशन इस सेक्शन पे शेयर फोर्स को इफेक्ट नहीं करेगी, यानी कि लोड ए पे है फिर वो हाफ तक गया फिर बी पे गया, उसका कोई इफेक्ट नहीं होगा इस डायग्राम।
क्यों नहीं? That is, you have that effect. This is the magnitude.
Okay. But
This is the magnitude of that load. So obviously this is actually the shear force. This is actually the shear force at C when your load is at particular position. So for example, if we are talking about this position, so this is the shear force. And this shear force, okay, so this actually the shear force at C when your load is at this position. Yeah?
Sir,
Yes.
can you label the axis of the graph?
Sorry?
Can you label the axis of the graph?
Axis of the graph. Say this is OO.
Like what is being represented on the x-axis and what is being represented on
No, on the x-axis it's the same. This is length.
It is the position of the load actually.
This is actually the length, but this is actually which is the position of the load. Yeah. So we can say yes. Let me write. So this is shear at C at y-axis, and on x-axis you have position of the load. That's what we have.
this displacement will be unity or
Yes. So this one, this is going to be 1.
Sir, like in yesterday you were trying to find the maximum reactions. So सर इधर वो maximum shear force की तरह आ रही है, वो point ढूंढने की कोशिश नहीं करेंगे सर?
Where would that maximum be in your opinion?
Sir,
at the point C.
At the point C.
So it will always be there where we
apply the load.
section, sir.
Yes.
Where we apply the load.
Where we apply the load.
Yes.
No, it will be the load is being applied on the whole beam.
Yes, sir. It is
Yes, but this is the maximum shear would be at the location where at the location of your interest. So that is the location where you have.
Sir, how can we make a result out of it? Like, how can we say that this bridge, मतलब ये इस डिजाइन का ब्रिज बनाओ जो इतनी shear force resist कर सके?
So the thing is that what happens is, yeah, there is a question. The question is that if we know, if we have any point of interest in between the two supports, okay, and we know that if we want to draw influence lines of that particular point, then at that point we will have maximum shear. Then how can we use it in the case of those structures which have got moving loads? Because we are always interested in finding out the maximum. So we don't know that at that particular section which we have picked whether that would be maximum or not. Yeah, that's the question. So normally what happens is, we haven't yet reached there. There are infinite sections in between these two supports, okay, and we can find influence line diagram for these infinite sections. Yeah, so out of these infinite sections, there will be one section which will give you maximum shear or maximum moment. How do we find that? We find that through something called absolute maximum shear, and those envelopes we will be dealing with later. Okay. So at the moment we are just concerned about one section. Okay. Now, so in the other class we will discuss how to find out the absolute maximum of particular shear or particular moment. Okay, I mean like along the whole beam when your load is running along the whole beam. Normally in bridge industry, what happens is that we try to find out our shear. We try to draw influence line diagrams for every 10th point along the length. In other words, we divide this whole length into 10 points and into 10, and then we try to find out the influence line for each and every points. Okay, so if for example if this is 50 feet long bridge, so we will divide it by 10. So at every 5 feet we will we will draw our influence line diagram for every 5 feet. If it's 60, yeah, so if it's 60 feet, then we'll draw it for every 6 feet. Okay, so that's how we normally find out, and then out of all those points we pick up the maximum. Okay, so we draw an envelope for that, and based on that we pick up our influence line. Yes.
So what if shear line between the points? For example, we are divided into 6 intervals, and
you will get the trend. You will get the trend. If you are missing it, you will get the trend, obviously. So if your maximum shear comes out to be in the middle of the points whose shear force you have already found. Okay, if it's not on exactly those points and it is in the middle of two critical points, then you will find it out eventually. How? By studying the trend. Okay, so you will find out, and normally, so you will get the whole picture by okay, so that we will do, don't worry. We'll find out the absolute maximum shear, absolute maximum moment, and all that. Okay, so that thing we will do. Okay, so now there are few things which we have to appreciate, and that is, let me, should I rub it off?
Yes.
The question is how to find out the magnitudes, various magnitude of interest along your influence line diagram. Okay, so if we have if we have influence line diagram for shear, which looks like this, so how much? So this one we have established because according to Breslau principle, this displacement is going to be unity. So we know that the overall displacement, which is this one, that's going to be 1. But how much is this one and how much is that one? That we don't know. Okay? But one thing we know, okay, that the moment is not released. Okay? The moment is not released. So what does that mean? If the moment is not released, then what is normally, for example, imagine, okay, let me put it in another way. Imagine I have got a beam and an internal hinge over here. Okay? What happens to my elastic curve at this internal hinge? Imagine I've got load applied on this side. I will have something like this. Yes, if I put load. Now, what this internal hinge does is it changes these slopes because there is a kink. Yeah, this internal hinge is like a kink. Normally, the slope of, for example, the actual slope on the left and on the right, that is same. Do you agree?
Yes.
The slope, if we have a curve, like for example, if I take something like this, yeah, and I bend it, so the slope at any point of interest, the slope slightly ahead and slightly after, that is at that section will be the same. Yeah, is that? Yeah, because it's not broken. But if I put a pin over here, okay, if I put a pin, if I've got a pin, then what happens is that in the case of pin, I can have it like this and another part like this, the link. Okay, I can have it in this direction. I mean, the slope keeps on changing. Do you agree?
Yes.
Do you understand my point?
Yes.
If I have got an intact section where bending moment is not released, then my slope at a particular point, slightly to the left and slightly to the right, that is the same. That's the definition of an intact curve, isn't it? We have done it in mathematics that if we have a slope of any curve, slightly to the left and slightly to the right, that slope is the same. But if we put a kink over there, or in other words, if we have two curves joining, so what I mean is that if I've got one curve like this and another curve like this, now this slope, so a kink will appear if it's not a smooth curve. This curve has got one equation and this one has got another equation. A kink will come. So then it is possible that this slope and the slope over here would be different. Yes. So the same thing happens. What moment does is, in your elastic curve, it brings that slope difference at that particular point. Do you agree? If you release the moment, there is a slope difference. Do you agree my point or not? Are you guys, is this making sense to you guys or not? No? Okay, what I am saying is that, for example, I have got a curve. I've got this is a curve. It is a sine curve, or it is a cubic curve, or it's okay, whatever you want to call it. I want to draw, I take any point. Okay? At this point, if I draw a tangent, and exactly, okay, very close to it, I draw another tangent. Okay? This angle will always be the same. Do you agree with me? It will always be the same because this is slightly, infinitesimally apart, okay, on one side, and infinitesimally apart on the other side, or towards the left or towards the right. Okay, they both are the same. But what happens if I have the same curve, and at this location I draw another line like this? This is a cubic curve. Imagine y is equal to x cube, and this is another line, y is equal to x plus c, something like that. So now what has happened, that at this point I would have one angle, and at this point I would have another angle. So there is a discontinuity in the slope at this point. And my point is that in the case of moment, when we put this internal hinge there, we have got a discontinuity in the slope. If you put an internal hinge, there is a discontinuity in the slope of your elastic curve. Do you understand my point? So, but this gadget which we have placed in the case of shear, that should avoid the discontinuity in the slope, because we haven't released our moment. Do you agree? Yes, so my point is, the main crux of this whole argument is that this line this line and these two lines should have the same slope. Do you agree? Yes, sir. So if this line and this line, so if this is my h1 and this is h2, so we can say that this alpha angle, okay, so we can say that this x, call it alpha 1, and call this alpha 2, okay. So alpha 1 by h1 is equal to alpha 2 by h2, okay. We can say that?
Yes.
And another equation is alpha 1 plus alpha 2 must be equal to 1. Okay, this slope alpha 1 by h1 and alpha 2 by h2, they must be equal, and alpha 1 plus alpha 2 must be equal to 1. So from this, can I determine what alpha 1 is and what alpha 2 is? Can I determine that?
Yes.
Because from here I can find out alpha 1 in terms of alpha 2 and place it over here. So I will find, so I should be able to find out everything in this influence line diagram.
Yes.
Is that okay?
Yes, sir.
Do you understand my point?
Yes.
Ask me. If it's not making sense, ask me.
Please repeat.
Okay, what I'm saying is, are we satisfied that the slope of this one and this one must be equal?
Yes, sir.
Are we satisfied?
Yes.
Do you agree?
Yes.
Okay. So if the slope of these two is equal, okay, so we can use the similarity of triangles.
Yes.
So this is similarity. This is the perpendicular by base of this one must be equal to perpendicular by base by this one.
Yes, sir.
Yeah, so that is one equation, and this one is, as I told you, based on Breslau principle. This whole displacement should be 1. So alpha 1 plus alpha 2 must be equal to 1. So I mean we can find out our alpha 1 and alpha 2. Do you understand my point? So that's what we have. Do you agree?
Yes, sir.
Okay, now what will happen in the case of moment? In case of moment, what we do is we place an internal hinge over here. Yes?
Yes, yes.
And if we place our internal hinge, we would have, normally we assume that we have got moments in this direction, okay, which are positive. Agreed? So I am assuming that my positive is in this direction. We would have something like this.
Yes. Tangential side.
If I put my internal hinge over here, okay, and I then apply unit displacement in my assumed positive direction. So what is that unit? What is that unit thing which I am applying in the case of moment? It's not a displacement. What should it be? I told you that in the case of shear, obviously this is a displacement. In this case, yes, this is the rotation. Theta 1 plus theta 2 must be equal to 1. This is actually, we are releasing the rotation, isn't it? So, as I told you that in this case, we have got different rotation. So, we make sure that this angle and this angle, this is equal to 1. Okay? So, you understand?
सही क्यों कर रहे हैं हम एंगल 1 की?
Because we are releasing the displacement. We are releasing the moment. Okay? So in the case of shear is a force. So for the force, the equivalent displacement is displacement which is in vertical direction, isn't it? If you have got a force produces displacement, isn't it? And moments produces rotations, angles, angular displacement. Okay, so this is a linear displacement and that's an angular displacement. So that's why we have introduced an angular displacement of unity. Do you understand my point?
Yes.
So now, how can we find out theta 1 and theta 2? So we know that if this is theta 1, this one is also theta 1, and this one is also this one is theta 2. Okay? So how should I find out my this dimension? If I know theta 1, Yes, so how? Yes, so we have to do rise over run. So tan theta 1, which is approximately equal to theta 1, is equal to this one. Imagine this is h. H by h1. This is again h1 and this is h2. So h by h1. Similarly, theta 2 is equal to h big H by small h2. Okay, and now we can put it in this equation and we can find out h1 and h2. Agreed?
Yes, sir.
So that's how we do this one. And in this case, we can easily draw our inference line diagram. Is that okay? Let's solve a problem and I think so it will become more clear.
सर ये स्मॉल h1 कितनी है? स्मॉल h1
Small h1 is this length and small h2 is this length. Because theta we are assuming very small. Shall I rub it off? Okay, let's draw shear force diagram for this one.
सर एक पिन है और एक
No, there is no pin. There is no pin. Yeah, this is okay. This is pin support. Yeah, but I mean, it doesn't matter whether it's roller or because your load is always vertical. Okay, so now for shear force diagram, shear force. What should we do? We should put that gadget over here. First of all, which location would have zero shear?
zero shear.
I mean the profile. Yeah. So zero shears. I mean no. At the support, at this support, this shouldn't move. Okay. This support shouldn't move. So your inference line should touch these 2 points. Okay. This support can move up and down. Okay. And this one can also move up and down. Up or down. This one can move up or down. Okay. So is that okay?
Yes, sir.
Now, if we put it over here,
Sir,
It will move up.
can you please state some magnitude of
no, what's the use of magnitude? Unity. This is, you are running a unit load over here. What magnitude?
consider one unity?
Huh?
सर हम हमेशा unity का
Yes, in the case of, that's what I told you, that in case of influence line diagram, we assume that there is a unit load which is running through your structure, and if whatever the magnitude is, then you multiply it with that, with your influence line, so you will get that particular magnitude of your interest.
Yes, sir.
Okay, so
It will move up.
now, if I put it over here, then what will happen?
It will move up. Influence line diagram.
So we have shear like this and like this. Okay. So should we get something like this? Should we get something like this?
सर ये ऊपर पॉइंट नहीं होगा ऊपर तो नहीं जाएगा करंट
So, according to our convention, we are assuming this thing. So we say that this one will go down and that one will go up. The same thing we did previously. But now you have got this overhang bit also, which is going to move. Okay, now let's find out the magnitudes. Okay, what will be the magnitude for shear force? For shear force, what do we call this? So this was alpha 2. Okay, so alpha 1 plus alpha 2 must be equal to 1, and alpha 1 over 20 plus alpha 2, no, sorry, is equal to alpha 2 over 10. Okay, so alpha 1 is equal to 2 times alpha 2. Agree?
Yes.
And then you plug it back in here. Alpha 2 plus alpha 2 is equal to 1. Alpha 2 is equal to 1 over 3. Alpha 1 is equal to 2 over 3. Okay, so this is alpha 1 is 2 over 3. This is 1 over 3. Agreed?
सर यहाँ पर अल्फा जो है वो 3 नहीं होंगे क्योंकि डिफॉर्मेशन जो है 3 जगह पे हुई है यहाँ पर अल्फा 1 अल्फा 2 और
What? I don't get it. What do you mean?
सर जो डिस्प्लेसमेंट हुई है वो 3 जगह पे नहीं हुई है
Which?
सर
Yes, come.
On the free everything.
No, this one, you have got nothing to do with this one. You are only concerned with your section of interest. The other things will follow. The other things will follow. So, this is your section of interest and it has got 2 displacements. Okay? Alpha 1 and alpha 2. So you can't have it. Is that okay?
Yes.
Now, what's the magnitude of this one? If this one is alpha 1 by 3, so what is this one?
The same magnitude.
Yes, because 10 and 10. So this one should also be 1 by 3. If this was a different length, then you would have found it. Okay, because this angle will be equal.
Yes, sir.
Okay?
Yeah, that looks perfect. Fine.
Okay, now what will happen in the case of moments? What will happen in the case of moment? So we should place an internal hinge over here, so that means that we should have moments over here. So I told you that if it's a hugging, then we have positive, and we are assuming the positive is on this side. Okay. So for example, so first of all, let's establish where we will have zero moments. This one and this one. Yes. So and this one should we have something like this? This is should we have something like this?
Yes, sure.
सर
Agree?
ऊपर क्यों गया है इतना?
Well, this thing will follow, as I told you, that if you move it, if you displace it in this direction, yeah, so this will follow. It's not going to be broken. It's not this. This one can move. So obviously it will move in this direction if you put a pin over here, isn't it? Yes? Yes. Now, let us find out. So, we said theta 1 and theta 2. So, theta 1 plus theta 2 must be equal to 1. And or what should we say? This by this. So let this be at, so h by 20. Theta 1 is h by 20 plus h by 10 must be equal to 1. Yes? So h is equal to 1 by 20 plus 1 by 10. So what is
20 by 3. 20 by 3.
Okay, that is my thing. And so what is this one? This is no, this is not. Yeah, this is theta 2. This is theta 2. How much is this then? This is also and that is 20 by 3. Does it make sense to you guys? Okay. Thank you. Can you switch it off? Give it a